So the next part of this lecture is going to be about maximum likelihood estimation. So this is a different way of constructing estimators. Okay, so far what we have done is an estimator, we said, is simply a function which is a function of the observations. We treat the observations as independent random variables, and an estimator is just a function of these. And as we said, the estimator is itself a random variable, and it has some distribution. We talked about unbiasedness and so on. Okay. Now let's look at a very different viewpoint. Okay, let me motivate it with a very simple example. Okay, so suppose we toss 100 coins. Okay, and we observe an outcome where the outcome is some sequence of tosses. Let's call it small x1, small x2 to small x100. Each of them is 0 or 1, and let's say 50 of them are heads, okay, or are 1, and the other 50 are 0. Okay. Now suppose I were to ask you intuitively, so the question is this a coin with probability of heads equals half, or is it a coin with probability of heads equals 1/3? Okay. So I guess many of you will answer that this is probably a coin with p equals half. Okay. Note that we can never be sure about this, right? Because even if it's a coin with probability equals 1/3, there is some chance that exactly 50 of them are 1 and 50 of the others are 0, right? Because there's always some chance that we were somehow we observed more heads than we were supposed to. Okay. Now you can, if you think about it, you can actually formalize this, right? So what we are asking is, what is the probability of observing this sequence x? This let me write x vector as the sequence. Okay. Okay. Given a certain value of p, right? So implicitly, this is what we are doing, right? So we are saying that let's at least if you think of my intuitive argument when p equals 1/3, I was saying that okay, if p was 1/3, somehow the chance of observing 50 out of 100 as heads is kind of low, right? So, and that is leading me to conclude that p equals 1/3 is not the right answer, right? Is not the right value of p. Okay. So, and the goal of this maximum likelihood estimation is to formalize this intuition. Okay. So let's do that exactly. So formally what we are doing is, what we are talking about is, let's compute the probability of observing this sequence conditioned on p. Okay. So if I had the probability of heads being some parameter p, now what is the probability that I observe this sequence given that 50 of them are heads, right? So this would be exactly p to the power of 50 times 1 minus p to the power of 50. right? Because 50 of my observations were heads and 50 of my observations were tails. Okay, and now let's find these values, right? So this function is called the likelihood function. The likelihood function is basically the probability of the data, which is the x, given some value for the parameters. Okay, so in this case there's only one parameter for a coin toss, which is the bias, and the probability of x given p, that is called the likelihood function. Okay, and in this case given my observations x, which are 50 heads and 50 tails, this is my likelihood function. Okay, let's compute the likelihood function and let's call it L of p, okay, just to give it some name, and it's a function only of p, as you will realize. Okay, so the way I wrote it here, it's a function also of x, but I am assuming that x is given to me, right? So the input is given to us. So let's compute L of half versus L of 1/3. Okay, so this is what we have been intuitively doing. L of half is exactly half power 50 times half power 50. Okay, let me write it as 1/4 power 50 or 0.25 to the power of 50. And what is this quantity? This is 1/3 power 50 times 2 by 3 to the power of 50, and this is equal to 2 by 9 to the power of 50, which is equal to 0.22 power 50. Okay, so one of these, L of half, is 0.25 to the power of 50, and L of 1/3 is like 0.22 to the power of 50. Okay, so what you will observe right away is that L of half is significantly larger than L of 1/3, right? Because the difference between 0.25 and 0.22 is not too much, but if you raise it to the power of 50, then the gap becomes pretty amplified. Okay, so this is why L of half, so the likelihood function, when you compute the probability of making these observations given p equals 1/2, that is much higher than the probability of these observations given p is equal to 1/3. Okay, and this can let us conclude that somehow p equals half is more likely than p equals 1/3. Right, and that's the basis of this procedure called maximum likelihood estimation. So it is also abbreviated as MLE. So MLE, the principle of this is that to estimate a parameter p, we look at the likelihood function, probability of data given p, and choose p that maximizes this. Okay, so let's do it in this example, right? So now in this example, what we saw is that L of half is much bigger than L of 1/3, right? But now you could ask, okay, could there be some other value, not half, let's say 3/4 or 2/3, whatever, which is maybe much larger than L of half, right? So maybe L of 2/3 is more than L of half, right? So we don't know, right? So now what maximum likelihood estimation is telling us is that find p such that L of p is as large as possible. Okay, so let's do it a bit more generally. Okay, so let's in fact have let's do this for general Bernoulli distributions. Okay, this is still a very simple distribution. So let's say we have our parameter is again p, And let's say now we have n coin tosses total, or let's be a bit more formal. Let's say that we have n samples from this Bernoulli, and let's call them x1, x2 up to xn as before. And we have the parameter that we'd like to estimate is p. So this is just a set containing p. I want to emphasize the fact that there is only one parameter that you're estimating. Okay, and now let's ask the question, what is right, so what is the probability of x bar given p? Okay, so to compute this quantity, you'll need to assume how many heads are there or how many ones are there in our observation. So let's assume that we have k ones in our observation and n minus k zeros. Okay, so then this quantity becomes exactly, this can be computed the same way as before. So it's p power k times 1 minus p power n minus k. Right? And now the question MLE is asking us, so this I will denote it by L of p as before. Okay, so this is the likelihood function, and it's a function of the parameter p. Okay. So now, what is the value of p? Maximizes L of p. Okay. Now, how do you find it, right? So note that now I'm treating k and n; these are all known values, and p is only unknown. So if I were to ask you, how do you maximize this function, right? So there's only one way to do it, which is by using calculus, right? So how do you maximize a function? So you set the derivative equal to 0, right? So use calculus ideas. So you set derivative equal to 0. Okay. Now this function is a bit messy to take the derivatives of, right? So what we do, which is in fact a very common trick, is not to work with the likelihood itself, but work with the log of the likelihood. Okay, so let's call this function, let's call it, maybe I will use a different letter. Let me use small l of p equals log of L of p. So this is called the log likelihood. Note that log is a monotone function, right? So taking logs preserves the order, right? So if A is more than B, and let's say both are positive, then log A is more than log B. Okay, so finding a value of P that maximizes L of P is the same as finding a value of P that maximizes small l of P. Okay, so let me use this word argmax. So argmax basically means it's the value of P at which a function becomes maximized. So what I'm saying is that argmax of L of P is equal to argmax of little l of P. Okay, and this is because of this fact. Okay, so this is what I'm saying. Okay, so if you haven't seen the word argmax before, I would suggest that you look this up. Okay. All right. So this is what we're going to maximize. So we're going to find the p that maximizes this L of p, and we are going to do this by setting the derivative equal to 0. Okay. So let's first write out an expression for small l of p so that we are all on the same page. So this is log of this quantity. So log of this quantity is what we are interested in, right? So log. So that is like log of p power k plus log of 1 minus p power n minus k. Okay. Because log of a times p is log a plus log p. Okay. Now again we simplify this, so this becomes k log p plus n minus k log of 1 minus p. Okay. And now let's take the derivative of L, right? So we need to take the derivative of L. How do you take so this is only a function of p, right? So dl divided by dp, right? So this is the derivative. So for this purpose k is a constant, so it's k times the derivative of log x is 1 by x, so this would be 1 by p plus n minus k. How do I take the derivative of log of 1 minus p? Right, so I have to use what is called the chain rule. Okay, so if I have, let's say, log of some function of x and I need to take its derivative, this would be 1 by f of x times the derivative of f of x, okay, which I denote by f prime of x, right? So in this case f is simply 1 minus p, so this would be 1 by 1 minus p. Derivative of 1 minus p is simply minus 1. Okay, so this is k by p minus n minus k by 1 minus p. Okay, and now I need to set this derivative equal to 0, right? So dl by dp equals 0 is equivalent to saying that k by p is equal to n minus k divided by 1 minus p. And now we can simplify this. This is equivalent to k minus kp equals p times n minus k. So let's now, we need to solve for p. Okay, so let's collect the values of p. So take this over here. So you find that k equals n times p, or p equals n, sorry, k by n. Okay, so this is the value where the derivative of this log likelihood vanishes. Okay. You have to check that this is actually the maximum, and let me not do that. That's a simple exercise, or it's also a very simple argument, okay, a more direct argument. Okay, so what this is telling us is that the likelihood is maximized when you set p equals k by n. Okay, so now that k was the number of heads and n is the total number of coin tosses, right, or n is the number of samples. Okay. And note that this is exactly what we had inferred before also, right? So p equals k by n is exactly the same as what the sample mean gave us. Right, because if you remember, the sample mean was simply this function which we had written down, right? And if k of these guys are 1, then this is the same as k by n. Okay. And now we are saying that this is exactly the same as what the sample mean would have given us. Okay. So this is a nice coincidence, and this is this holds for a few simple cases, not all the time, but in some cases there is this nice property that what we get via sample means and so on also maximizes this log likelihood. Okay. And this is how the maximum likelihood estimator works in this simple setting of a Bernoulli. Okay. So you can ask this kind of a formulation for any estimation problem, right? So let's say I have real data points. So let's say I have data, so x1, x2. Note that I'm writing small x1, small x2 up to small xn because these are actually data values. Okay. Capital X's I usually denote by random variable. I mean, I usually use for random variables. Right, so let's say I have these numbers and these are real numbers, let's say, and let's say drawn from a Gaussian, right? So from some Gaussian of unknown mean mu and unknown variance sigma square like I have before. Okay. Now you can also write down the likelihood function here, right? So which is probability of observing these values given mu and sigma square. Okay. And how would you write this down? This is now a very messy expression, right? Because it would be basically uh, so earlier we just said, okay, implicitly what we did was we said, okay, what is the probability that x1 was observed, and if x1 was heads it was p, if x1 was tails it was 1 minus p, right? So now the expression for this, what is the probability of observing x1, is now a bit more complex, right? So this is the PDF of the Gaussian, which was 1 minus sigma, 1 divided by root of sigma root 2 pi e to the minus x minus mu whole square, x1 minus mu whole square by sigma square. This was for x1. Okay, you have to multiply this by sigma root 2 pi, the same thing, x2 minus mu whole square by sigma square, maybe there was a 2 also, okay, and so on. Okay, and you have to multiply all of these quantities, right? So this is the probability of seeing the first point, this is the probability of seeing the second point, and so on. Okay, so now note that this is why this log likelihood really is nice, because now let's call this the likelihood of mu and sigma squared. This is like this. Note that now the likelihood is a function of two parameters, because now there are two parameters, mu and sigma squared. Okay. So the nice thing about the log likelihood is that now if you take logs of these quantities, they all add up because we are taking a product of all these terms. Okay, so little l of mu and sigma squared would be, these quantities would remain the same for all the terms. Okay, so this would just be n times log of 1 by sigma root 2 pi plus the nice thing about logs, log of e power x is just x, right? So this would just become minus sum of I going from 1 through n of xi minus mu whole squared divided by 2 sigma. Okay. So the log likelihood of this Gaussian, in the case of a Gaussian, becomes extremely simple. Okay. So it's not extremely simple, but it's way simpler than, let's say, the likelihood itself. Okay. So, and now suppose I am given these observations small xi. What I'm asking you to do is try to find mu and sigma square that actually maximize this entire expression. Right? So this is something that it's something which is maybe not as simple as an exercise, but it's still doable. Okay, so let me not do it because it's slightly outside the scope of this course, but this is a general principle. Okay, so the general principle of maximum likelihood estimation is you write down this likelihood function. Usually you take the log, so you write down this log likelihood function, which is probability of data given the parameters. Okay, probability of observing the data given the parameters. You look for the parameters that maximize this, and often you do it by finding an expression for log likelihood and then differentiating it. Okay, so in this case, if you end up differentiating this expression with respect to mu, you end up with this nice observation that mu, or rather mu that minimizes this, so estimated mu is actually equal to x1 plus x2 to xn divided by n. Okay, and this is exactly the same as the mean, sample mean. Okay, again this is a coincidence. Okay, but yeah, so this is the nice fact that even for the Gaussian case, the mean turns out to be exactly the same as the sample. Okay, and right, and this is this general principle of max likelihood estimation. It's very general. It can actually be used for in many settings, and it's commonly used in machine learning for parameter estimation. But what often happens is that this likelihood function is often very difficult to maximize. So people end up using a lot of heuristics for this, and usually this estimation is done computationally. It's very unlikely that you will end up with a closed form, a clean closed form like this. It happens only in the case of simple random variables like Gaussians, like Bernoullis, and so on. Okay, so this is something about max likelihood estimation, and yeah, we won't talk too much about this in this course, but you are welcome to read more about it in the textbook.